So we have the next talk, the last talk of this session. The number 2 CubeSat webinar will be given by Dr. Antti Kestilä. Am I correct? Am I pronouncing it correctly?
Yes, yes.
Lessons learned, right,
okay.
from Aalto
Yes.
studies. I fumbled your title, I thought it was too long. I cut this part.
Yeah. No problem. It's a bit of a hot pot of different topics. I wanted to give a sort of an overview of.
Okay, you are talking about your FMI lunar mission activities. So
yes.
I'm going to ask you to give another talk at our other mini moon webinar.
Oh, that would be nice. Yeah.
Right. Yeah.
Thank you, Professor Ip, for inviting me here to give this presentation. So, as I mentioned, this is a bit of a hot pot of different topics. Basically, I wanted to first start off with just giving some lessons learned and my own experiences with the Aalto satellite. So, it was from the time when I was still doing my PhD in Aalto University before I finished my dissertation and moved to work to the Finnish Meteorological Institute. Then after that, I want to give a bit of a overview of the more recent activities and projects we have. And the common thread here is small satellites, of course, and CubeSats. So the lunar mission activities of FMI, I wanted to present quickly a small package that will be delivered, hopefully will be delivered with a rover or alongside a rover mission to the moon. And then at the end, I wanted to give an overview of our current project regarding how to 3D print satellite components, specifically small satellites. So yeah, that's in a brief summary. So I've made about 15 or so slides. These slides were made as a sort of an overview, so I won't go into the details because a lot of details I'm covering regarding, for example, these small satellites. I'm trying to cover briefly the lessons learned from 3 projects. So basically, we started at the Aalto small satellites. We started about. Oh yeah! By the way, if you come up with any questions and so on, I'm also okay if you ask them during the presentation. There's, of course, at the end of the presentation, there's a Q&A time, but you can ask during the presentation as well if something isn't clear. But it's sort of a starting slide. Here you can see the currently 3 satellites that have been built and launched from Aalto University. On the right side. So here, these are all pictures I've taken during the years myself or been present. So it's sort of a personal journey through past experience for myself as well in this presentation. So here you can see the 2 Aalto 1 and Aalto 2 satellites in the laboratory. While we were still at the old laboratory facilities, then later on moved to new facilities. So here they are alongside. So they were built. Aalto 1 was started in 2009 and 2010 around about, when me and Jan Prax were discussing whether it would be very cool to start a small satellite, to try a small satellite project. And I had started in Aalto University, I think it was in late 2009. I had just graduated from Delft Technical University in the Netherlands and came back to Finland. Well, we started the Aalto 1 project, and it was slowly, 2009, 2010, it sort of slowly started to roll forward. And a few years later, we also started Aalto 2. Which was part of the, I'm not sure if you've heard about the QB50 CubeSat constellation. Then it was a project funded by the European Union and run by Von Karman Institute in Belgium, if I remember correctly. Their goal was to send 50 CubeSats I don't know if they achieved in the 50 CubeSats, but at least, it was a very interesting project to cover the atmosphere, or study the atmosphere, and with all of these CubeSats alongside, or through all these CubeSats. Then, of course, as presented previously by Esa, started the Suomi 100 project. Remember, we started in 2017, but I think we started discussions already a bit early in 2016. But a few years after, at that time already, the first two Aalto 1 and Aalto 2 satellites were starting to be already in an engineering shape. So the goal, basically, in all of these projects was teaching, of course. As it's a university, we wanted to teach students how it is, what the space project is, how you can build satellite, test it, design it, and so on. There was a lot of technology demonstration goals as well. So we had a lot of payloads that were built either by us or by partner institutes. And we also tried some science, especially with the Suomi 100 satellite. There was at least in my view, a sort of a goal of us actually trying to do some new science, which wasn't that much of a case with the Aalto 1 and Aalto 2 satellites. Maybe QB50 was a bit of a science demonstration, or there was a science goal, but the first two satellites were primarily, the idea was science. Then these three projects from Aalto 1, Aalto 2, and Suomi 100 gathered a sizable amount of students around them, and it's sort of some sort of a critical point was achieved in terms of people and activity, and then two spin-offs, commercial spin-offs came out of these two projects, which is the Reactor Space Labs, which mainly concentrates on CubeSats and CubeSat-ish small sat projects. I think they have one satellite they've launched successfully. I think it works okay still, and then they are planning another one, if I remember correctly, now to launch. Then we have ISA, of course, which is concentrating on SAR small satellites, and they have launched several satellites, if I remember correctly. I'm not sure which one of them still works of the satellites. The first one last few months, and the other ones I think work successfully. Some successful radar pictures have come down from those satellites, and it has gathered, or both spin-offs have gathered a sizable amount of investments and so on. And then Aalto University has several CubeSat projects in the works now, still or coming. So Aalto 3 is in the works. I haven't heard recently from it, but it's a student project like Aalto 1 and Aalto 2 as well. Then we have the For Sale 1, 2, and 3, which are CubeSat projects funded by the Finnish Academy of Sciences, if I remember correctly. I'm not involved with these. I don't know much about them, as at that time I already moved to the Finnish Meteorological Institute. But so there's a lot of activity now going on with these small satellites, and I think it's a sort of a interesting way for small countries like Finland to get a bit of a foothold with in the space sector. So instead of Finland has had in the past a lot of very good and high quality space instrument development. And in the end, if I remember correctly, in the end of the 90s, beginning of the 2000s, there was a concerted effort to make a micro satellite here, but it did not go past the preliminary phase, as it was pretty expensive, and it was like, I think, several tens of kilograms, if I remember correctly. So it was still at that time so significantly bigger than these CubeSats. So these CubeSats open possibilities and open new doors. So going further with the Aalto satellites experiences, here you can see on the right side where my mouse points different, different versions of the Aalto 1 satellite that we built throughout the years. So I took this picture in like years ago. There was a workshop which we rounded them all up like this. That we started from a little milk carton. I'm not sure if you can see this how well, but if you can see, this is actually a milk carton that somebody painted something like resembling like solar panels and a name. And then it sort of a bit by bit started, and we built these, and it was very important to have these mock-ups and funny mock-ups, because it sort of gave concreteness to the project, which is important not only to get funding and to get more interest, but also to just get how can I say this, keep the sort of goal in mind that one day we will build this satellite and it will become an actual satellite and so on. But in a way, if I can come back to the lessons learned, we started a bit the other way around. So we started with Aalto 1 being a complex 3-unit satellite, and it took about 7 years, around about 7 years of building it and testing it and so on. And it had 3 specific payloads, which are the results of which I'll come to a bit later. So the spectral imager, multispectral imager that creates sort of a same image but of different frequencies by VT, the Finnish Finnish. I don't remember the name in English, but Finnish Research Center, and then a radiation monitor by University of Turku, and then a deorbiting plasma break by Finnish Meteorological Institute, which besides these 3 payloads, there was also a homemade GPS that we built by ourselves, pretty much from the component level, and a home-built computer. So the onboard computer that handles all the data transfer between the different subsystems and basically controls the satellite. We also built the radios for the Aalto 1, and most of the subsystems we built ourselves. Here you can actually see here the 3 payloads pictured. So they were in themselves pretty complex as well. So then Aalto 2 was actually a 1 payload. The QB50 gave us a payload package that gave Aalto a payload package that then we would fit into a 2U satellite that we ourselves built. And it took 5 years then. So I don't know if you can see a pattern here. Then finally Suomi 100 was then 1 unit, in which we built the RF instrument and ourselves, and this camera came from the bus or the satellite structure commercial provider, and it took around 1 to 1.5 years. So you can see the pattern here. In a way, I think one of the lessons learned here is that we should have started with Suomi 100. In a way, it was a much more sort of a quicker and also a more well-organized project, the Suomi 100, compared to Aalto 1 and Aalto 2. And in a way, we could have done all of this the other way around. So start with Suomi 100, then go to a 2-unit satellite, then finally go to a complex 3-unit satellite, and so on. But when we started this the other way around, so to say, maybe it gave us, in a way, it was a very steep learning curve, but it kickstarted a lot of activities on the other side. So however you want it's a strategy to be chosen then by. So all of these satellites had several commercial off-the-shelf systems. Aalto 1 had a electrical power system, power and control system that was commercial off-the-shelf, and if I remember correctly, what else there was? I think that was it. Yeah, everything else, including the solar panels, well, not the solar cells themselves, but the solar panels where the cells were integrated, was pretty much somehow built by either Aalto or our partner institutes. It's mostly the same thing with Aalto 2, except for the QB50 measurement package or the payload package that they gave us. So only 100 had more commercial off-the-shelf systems, including the visual camera that takes pictures, and most of the structure, the bus structures, I think the solar panels were made. Then solar panels, power system, radio, yeah, pretty much most of the stuff was built by commercial or out of commercial off-the-shelf systems. So we bought them commercially, this has a good side and a bad side. The good side is with the Suomi 100, the development was fast, and we could concentrate on the so-called important elements of the. So developing our RF instrument and then saving up resources for the actual operation, which is a significant part of the satellite mission and quite important, and often tends to be forgotten. I've noticed with CubeSat projects. But on the draw side, on the bad side, in the case of Aalto 1 and Aalto 2, the commercial off-the-shelf systems weren't really that good. So in the end, I'm a bit, maybe in the recent years, in the recent few years, the level of the commercial off-the-shelf system has increased or improved. But I'm a bit skeptical based on these my experiences, and the commercial off-the-shelf systems were often just as bad as our student-made system, or could be just as bad as a student-made system. The quality could be bad. For example, the electrical power systems in Aalto 1 had all kinds of quality issues with the soldering, basic stuff like this, could not operate. Some basic functionalities like charging was very difficult to achieve, or and so on. And once we had bought these commercial off-the-shelf systems, then we were sort of stuck with them. We couldn't run away from them. We had invested the money, and we didn't have much money, and it tied us up with these systems and all the bugs and features that they tended to have. I think somebody earlier, I think it was Christian, asked about COTS, commercial off-the-shelf ground systems and ground stations. I don't have direct experience regarding them, but I would be wary and careful about using commercial off-the-shelf systems, just because the quality, from my experience with COTS stuff, tends to be not as good as one hopes it could be. Then my other main point, my other lessons learned point, was something that basically I think Esa already bit touched upon in his concluding slide, was that the student workforce is also a plus and a minus in a way. Of course, this is the idea here, is to teach people, so we have to involve students. Of course, that is all quite necessary and a primary goal of these projects. But altogether, here on the lower right side, you can see an image of the once Aalto 1, I think, was launched, of the team at that point. Altogether, these Aalto 1 and Aalto 2 projects involved more than 100 students, which was quite a lot. And it created a lot of challenges, because the students tended to often were very, they smart and capable people, but often, of course, they had actual studies to attend to. and work with and theses to finish and so on. And often they also left to work and so on. So there was a constant influx of new people and constant outflux of old people. That let the old people, the veterans, took away the knowledge and experience, did not often write good documentation, and the new people had to almost start from scratch. So we ended up with having to build layers upon layers of the same system sometimes. Like, for example, the ground station. There was like 3 iterations of the ground station and the software and so on. And in a way, with that presented a significant difficulty, especially when you had to sort of manage all of it and push people and ask people to work on the different subsystems and so on. So yeah, that was a challenge. So with S100, we had less people involved, but they were very motivated and they were all still students. So in a way, there was a bit of a pre-check. We didn't check or filter in any way, but we sort of the team involved was, I think, more or less somewhere within 10 people or so, and it was everybody stuck to the project within the 1 to 1.5 years that it was running. And it's sort of that way everybody knew the satellite quite well and were able to work with it. There was no problem with constantly losing old students with their knowledge and having to retrain the new ones. So that worked quite well to keep a sort of a core team one way or another involved with the project as long as possible. So it's another very, very important lesson that we learned. So another major part is testing, of course, as Esa mentioned. Here you see a picture of Aalto 1. I'm not sure how well do you see it. I hope you see the details here. There's and I wanted to add this picture because it shows how complex, from how complex starting point we started. So we had an engineering model and a flight model, while Suomi 100 had a proto-flight model, meaning that it was like the engineering tests were done on the same flight model that then would go to space, mainly because of funding and funding related issues with, it was quite expensive to buy an engineering model and flight model separately. But Aalto 1 had one stack which was stacked on, say, like this along the this direction, and then there was another smaller stack which had the plasma brake, which was stacked 90 degrees with respect to the first one. And I could say that this is not, later on, I could say that this is not really a smart thing to do, maybe with a CubeSat, because it presented all kinds of integration and so on, like interface issues, which was a major pain later on when we had to then test it. So we, Aalto 1 and Suomi 100 went quite exhaustive tests. So we did integration tests, meaning we connected all the blocks, tested them, how they work together, if they work well, how they work, and so on. Quite a lot. And in the case of Aalto 1, part of that was because in a way it was unintended, because new students came in and they had to sort of relearn the system. So we sort of did redundantly integration tests. But with Suomi 100, the integration tests were then already quite coherent and planned. Then vibration and thermal vacuum, which was also important. For Aalto 1, we did them twice. Yes, the vibration and thermal vacuum. For Suomi 100, we did only once, as we use a proto-flight model. We did a lot of functional testing, so meaning software. Different subsystems were tested for functionality and so on. And most importantly, we did sort of a different complete link communication test. So what I mean by this is we took the engineering models, or in the case of the Suomi 100, we took the proto-flight model and we tested it directly with the ground station. So we tested the whole link from the ground station as if it would be in space. In the case of Aalto 1, we brought this, I think it was actually the engineering model you see in this picture on the lower upper right side. And brought it, the engineering model brought it to a hill like 20 kilometers away and tested it with the ground station directly. And so this was quite important because we could get a bit more comfort that once we launch it in space, the whole link, the radio link, will be able to work, even if it would be low link or bad link or so on. It gave us a bit of comfort in that respect. And so we also did, well, as I mentioned already about S100 camera calibration tests. These were quite important. And I think the manufacturer of the Suomi 100 bus on the structure actually commented that the pictures that the Suomi 100 satellite was able to make, so what ESA previously showed, were actually pretty good quality, even from their point of view, when they compared it to the other missions that had used the same camera. And so, but another interesting lesson learned would be to also the software component tests. Component, what I mean is the sort of a unit tests and software unit integration tests and so on. But we also, what we did was we at some cases with Aalto 1, for example, the ADCS was commercially manufactured. And so we were able to, or bought from a commercial manufacturer, we were able to add, because the satellite onboard computer was built by us, it had a onboard Linux system, space Linux, if you will, in it. So we were able to run a rudimentary command line and to it, and SSH. So we were able to let the commercial manufacturer test their own ADCS remotely via the internet, while the satellite was in the laboratory in Aalto University, which was pretty nice because then they were able to do their own rudimentary tests on the ADCS. The ADCS didn't work. Nevertheless, the ADCS did not work as we expected once the satellite was in orbit. But it was, I think, an interesting point to bring out that there's sort of flexibility these days in terms of testing. So yeah, lots of testing. Then the deployment and launch experiences. So as I mentioned, there was a lot of delays for the S100. But also with the Aalto 1 and Aalto 2. So Aalto 1, we had almost 2 years of delay. We switched launches. If I remember correctly, we were originally supposed to launch with the SpaceX, but then SpaceX at that time exploded one of the launches, and then we had to launch with the Indian PSLV. 2 years of delays, during which time we had to go twice and recharge its batteries in the once we had already integrated it with the quad pack or with the commercial deployment system that we used. So what in the end happened was, technically speaking, Aalto 2 was first in space in terms of the Aalto satellites. It was launched a bit earlier in 2017 from the ISS after several delays. Unfortunately, Aalto 2 failed just a few days after the launch, and the expected failure was the electrical power system. My personal feeling is we tested Aalto 1 and Suomi 100 quite a lot, but Aalto 2 wasn't really tested that much. And so the failure, I think that attributes to the failure. But Aalto 1 was then launched I think it was like 2 months after Aalto 2 was launched, finally, after years of launch delays. And then in a quick succession, at that point, we had started already Suomi 100, and we were able to launch it in 2018. I think it was December 2018 then. So, after a significant delay there as well. All of them were sort of a launch with this, Aalto 1 and Suomi 100 were launched with this quad pack system. And here's an image of the Suomi 100 being added in there. So this is the commercial middle company called Easy Space in the Netherlands. We went there and stacked them in the quad packs. Aalto 2 was in a more specific, it was the NanoRack system by ISS. Overall, the lesson learned here, I think, is that the whole launch period was really a difficult period. It drains so much of our resources, just keeping the knowledgeable people around, that it really is something I really can't, the lesson learned here, I think, if I need to sort of summarize this, that you have to sort of prepare mentally and funding-wise and project-wise for the launch and the delays that it will occur. Somehow make it so that your project team is able to consist or keep intact while you just wait. And you have the knowledgeable people to operate the ground station and the satellite still around once the launch happens. Then going to the ground stations and the lesson learned there. So as I mentioned earlier, there were several ground station iterations were built. So here you see on the left or the center upside, here's the original ground stations with a UHF, VHF antenna and a separate S-band antenna. Because Aalto 1 has also an S-band downlink antenna and a radio, which was built by us. I'm still not sure if they ever managed to actually use the S-band, but the VHF, UHF works quite well with Aalto 1. So, however, as all of these launch delays occurred, our faculty moved their building. So we had to move the whole ground station in between. So here you see the new current building where the Aalto faculty is located at, and here you see the students lifting the satellite, the antennas there. And it was a significant project in itself. So we built several ground station iterations because of delays and moving, and just because new students came in and old students did not adequately document, and it ended up as a sort of a hodgepodge of software, layers of software and operation strategies and so on. And it still to this day requires constant maintenance. So it really requires I think like in December, the rotator in this antenna broke, and it's basically it broke the rotator motor, and the cabling, if I remember correctly, broke again, like for the fourth time or so. So it just requires constant maintenance in all parts of this hardware parts, and I'm not sure, like there just is not commercially available decent systems you can buy that can withstand long duration, long maintenance when built in this sort of a student context. So here you see an image of how it is operated. You have a student sitting in this room, both Suomi 1 and Aalto 1, next to a big rack of servers, and then operated basically whenever it is on. I think or visible. The satellites are visible in the ground station. I think at least Suomi 100 has been automated in a way that now it can be remotely operated, so that it can be automatically scheduled to do the operations. So it doesn't necessarily need a person there to manually operate it, which was a big relief, and it sort of helped with the operations quite a lot. So in the long run, the lesson learned here is not only that the ground stations are difficult hardware-wise and constant maintenance is needed, but also that probably the most difficult part is actually the constant year-long operations. Once you're able to launch the satellites and they work and everything is operation, for years you need to have the knowledgeable people around to, or then retrain the new students to then operate these satellites, because Aalto 1 and Suomi 100 are still to this day are operational, and their link is relatively slow. So it needs, you have a slow trickle of data and you need somebody to run it constantly. So other lessons learned from the operations, there was we needed to coordinate a lot with the neighboring satellites first few weeks, because they will all launch in one launch vehicle in a sort of a one swarm or lump, if you will, and they're very crowded. So there was tens and tens of satellites on board one launch. Here you see, I think this is Aalto 1. Our sort of this is the image here is a rainfall of the RF frequency or spectrum. And you can see our signal. This was a big relay because we knew it was alive, but then it's a huge crowd. Here you see, I don't know how well you see the picture, but you see several like red patterns. So all the satellites are crowded along with ours, and it sort of makes it really difficult. Then the frequency coordination process, as Esa discussed a bit, it takes time, but it really takes time. It took at least a year. It was a lot of bureaucracy and mostly waiting for the bureaucracy, the wheels of bureaucracy to turn, at least here in Finland. And the frequencies are in really heavy use and they're very crowded. There's like, for example, here in Europe, there's a problem that there's, I don't know, NATO radars in Central Europe or somewhere that really make the bandwidth difficult or listening to our signal difficult among those powerful signals when the satellite comes from the south, so from Central Europe. And once we get it running, those operations figure out all the sort of a basic initial problems, then the payload results, the payload data comes really slow. So here we had the first Aalto 1 image. It was really nice and we were lucky that it worked. From the visual, the spectral image, which had a visual part. Here's the same visual spectrometer that took a series of pictures. The satellite was a bit sort of a tumbling, so that's why we sort of made a mosaic of pictures on the lower right side. But it took like weeks to get these done. And which time we just had to download and download and download and so on. And these were compressed also. See, it's a bit more images from the visual spectrometer. You can see the visual spectrometer here has some vis spectral bands. So the visual spectrometer takes cubes, if you will, of same image, but from different frequencies. So here you see the color frequencies, and here you see the spectrometer going a bit further. And the idea is to, I'm not sure if you can see it well, but here is another picture. The spectrometer has taken a lot of frequencies from the same geographical location. And here you see a little square which shows the river and details from the river. So the spectral image is able to sort of give some tantalizing details about each pixel in the image and so on. But these images really took a very long time to get down. Here's the radiation monitor in turn working. So here's a sort of a overview map of the radiation areas it was able to survey, if you will. So here you see the famous South Atlantic anomaly and then the radiation zones around the poles. And this one took, as you can see, maybe from the image, hopefully you can see these sort of small lines. So these are the individual's flight orbits. So it took another very long time to build this image. The plasma brake also works, and it has been sort of semi-deployed, but I don't think it has been. I was not in Aalto at the time when it started its operation, so I'm not sure if they've actually even tried to still deploy it. So that payload is still in like initial, I think, phases or after all these years. This is basically my last slide regarding the Aalto satellites. I would like to make a quick check whether the links or the presentation works. Professor Ip, do you still see the screen and my voice? Does it work or does it hear well?
It's fine.
Okay, great, sir. Okay, good. Just to check. So, the this was a lot of stuff, a lot of experiences, but basically, after these small satellites projects, we noticed there were good sides, of course, and one thing was that there was this modularity to small satellites, and modularity, and if you will, a sort of a design standardization. So the next project I want to show is the lunar activities that we wanted to that FMI has been working on. So the idea is to build in a ESA project a small 5 kilogram box that will be deployed by a rover in a future ESA mission. It's called Lunar In Situ Sensor, LINS, and the idea is to deploy it in the Schrödinger crater near the South Pole. Payload includes camera, hyperspectral imager, microdosimeter, soil thermal probe, magnetometer, dust sensor, electric field sensor, and a seismometer. So quite a lot. So nevertheless, as you can, here's an very early picture of how it looks inside. I'll show you a more detail a bit later, but you can see a bit of the idea here, the small satellite stacks. So the idea here was to build in a sort of a small satellite mentality of if possible, buying it commercial off the shelf, or at least using some sort of a standards to build the subsystems to be able to relatively quickly build this kind of a this kind of a package that can be deployed on the moon. Of course, the moon is a very different place than the surface of the moon is a very different place than low Earth orbit. Here's the Schrödinger crater. But visualized in terms of I think this was the monthly solar energy influx per pixel. So you can see there's permanent dark areas, there's some semi-dark areas, and this is, I think, 100 or so, some hundreds of kilometers of scale. So it needs to survive whether it is dropped in a shaded area or in a sunshined area. It needs to survive in a large range of thermal and solar environments. So here's a more recent image of the solar package. So this is I have to mention, this is as an ESA project, this is still a preliminary project. So we're still sort of designing this, and we have not started building it yet, but hopefully we will start in the next phase to actually build this package. So here a bit, you can see the stack approached. And it's the goal here was to basically, well, not the goal, but the design principle was to not only use small satellites, but then also add in the very demanding lunar environment considerations. Like, for example, we had to consider the thermal aspects like wrapped MLI, curved corners, cold compartments, warm compartments. How the boom works, does it work for the intended? The goal is to have a 2 years mission here with this type of a package, and there was supposed to be 4 of them. This preliminary design deployed all over Schrödinger crater, and so that had to be as it was a new factor that we normally did not have to consider with small satellites. Design principles, if you will, when they were launched for low Earth orbit. And basically the design, well, to a bit reiterate, the main design question is that were new compared to the small satellites principles was survival during lunar night. So you could drop to minus 170 degrees. So then we had to consider many factors, like, for example, using anything from specific insulation to paraffin, so wax, inside the box and so on. So heating and thermal control, also energy production, because the lunar night is long and cold. So whether we could do only solar panels or batteries, or we could use a radioactive heating unit, RHU. So we have been considering in that kind of a isotope-based unit. I don't remember what's the most recent design is. Will it include the RHU? But it sort of is in consideration. And then, of course, energy storage. And all of these points, as I mentioned, are really a challenge to small satellite technology. So when going to the moon, it is smart to use maybe small satellite technology and the principles, but then the environment changes so much that it creates a whole new range of challenges for this that type of a mission. Then as my last topic, I have a few more slides only. Then regarding the small satellites, we also have been investigating how we could actually make it manufacture them a bit more flexibly and quicker and better, basically. The goal here was that, well, in one way you can get more payload and instruments and missions to space by making a better rocket, of course, but on the other side you can also make the satellite and the payload and more lighter, and maybe because it's 3D printed in this case you can also make it more custom designed so it can fit better into the fairing of the rocket. So we went from that approach. So we have been working on a project called HighPeak, which wants to print from 3D print from thermoplastic PEEK material that has conduction in it. Different components, not only for small satellites, but for generally, different components. But in a way, the side goal here is to make small satellites easier and better. The official goals are that we make them lighter, we give them ESD protection, and generally make them the shape more flexible as you can 3D print it. As I mentioned, the printing material is conductive, so all of these boxes can conduct. The PEEK itself conducts and can sort of discharge the static charge that tends to pile up on the surface of the metallic or the non-conducting components. So if it were from normal plastic, it would maybe have a bit of risk to pile up this static charge. So when we make it the plastic conductive, it takes care of that. And one of the things we have noticed, it's surprisingly good mechanical properties nevertheless. Of course, it's not really the good. Of course, plastic is not as good as aluminum, but plastic per gram or so mechanical properties, for example, strength properties per gram of mass when comparing baseline metallic and plastic are better for plastic. There was one results, the current results, and this is an ongoing project, show that this almost twice as better in terms of mechanical strength. And still it's much lighter than the aluminum part. So here's an example. We printed out, we took a baseline metallic box. This is an OBC housing for a big ESA mission. We designed it into 3D printed part, printed it. We made different versions of it. We have tested it in vibration testing, so with the electroshaker bench. And here's another example of a bracket that holds honeycomb walls together. So these are very common and ubiquitous through satellite missions, especially telecom missions, to which this project officially is sort of aiming for. As it's ESA Artes is the telecom ESA telecom satellite subdivision of projects, if you will. So they're full of these kinds of brackets to hold the wall. So you can sort of print them out from 3D printed, and you make them in a way much lighter, and still they can withstand even better than the aluminum parts. Here's another few examples. This is from the Sentinel-1 mission, ESA Sentinel-1 radar mission. So this is the RF sort of a relay component that was a basic baseline metallic, and then we printed it in from a conductive PEEK and made it much lighter, about 50% or so lighter. Here's also what Esa showed a bit earlier. Another point here is that maybe is that we can also do flexible designs and fast prototyping. So the Suomi 100 satellite, this is the very early prototype. I printed it with the home 3D printer. So this was it was actually crucial because we could then show it to people that, hey, this is what we intend to build. And then here is an image of the satellite with a 3D printed antennas that this, I think Isa showed in previous presentation, where the actual antenna, RF instrument antennas, are encapsulated in sort of a 3D printed encapsulation. This was important because we were able to fit it inside the very tight margins this satellite has, because it goes into a quad pack, and so the next satellite will be above it, literally. And so there's only like a few millimeters of space there. And this would not have been possible without 3D printing. So this really enabled us to do something new in a very CubeSat type of a problem or situation, if you will. This is my final slide. We also are trying to push the envelope a bit. So we wanted to make complex circuit, so really a sort of a electric circuit with microcontrollers and so on integrated. We wanted to make it into a 3D printed component. So here's some. This is still ongoing, but some early images. This is a very early picture of how we 3D printed a part here, and then we added LEDs. We coated it with a very thin copper coating and created the circuit patterns on this coating. So we were able to get two LEDs working on it. Later on, now we have been able to actually integrate a microcontroller into a 3D printed part. And notable here is that this is all, the copper is again coated. It's about 10, 20 nanometers, but notable here is, I'm not sure if you'll be able to see from the picture, but here you have a tunnel going through this prototype, and it connects this ground line here, the black line. It goes through the part and it connects to the microcontroller. And here's the same CAD model for the same prototype. The idea is to basically use these two types of materials, thermoplastics. One retains the coating, and the other one is not able to the coating is not able to coat on top of it, catch it, so to say. And so it creates a sort of a selective coating. Well, that's the goal of the project, to create a selective coating which can just be coated, and then it works as a 3D circuit. So the final goal is to basically print any kind of part, 3D print, and then sort of integrate circuits, complex circuits on the top layers, and then even connect inside circuits that have been sort of added inside the 3D printed parts, encapsulated, if you will. And this this basically, we would be able to add some functionality into 3D printed parts, say thermal temperature measurement, or accelerometers, and so on. And it's one of the other applications also include, we've been extending solar panels, making this way solar panels, and RF applications, for example, antennas, because with 3D printing you can make very complex patterns. So the baseline to which this coating would go can be made very complex. I show here a block, but you can make it, as you probably have experience on it or have seen 3D printing, you can make any kind of shape, basically. And you can make complex antennas, which you could otherwise not really easily make, or at least not cheaply, if at all. So yeah, that's pretty much my presentation on these three topics. So thank you very much, and if you have any questions, please do ask.
Thank you so much, Antti. So anyone have questions, please unmute yourself and ask the questions first. I think that it's getting more and more interesting, of course, you spend a lot of time talking about your past experience of Aalto 1, Aalto 2, and Suomi 100, and those are very important, lessons learned. But then the last 10 minutes, you talk about this your moon mission, and then you talk about the 3D printing. So I'm just wondering, how did you get into all this?
I think it was a bit of a continuation. So the moon mission is based on because the Finnish Meteorological Institute has previous interplanetary instruments. For example, they have built instruments for Mars missions and so on. So this lunar mission was a sort of an extension for that. And then the new part comes from small satellites. So the Finnish Meteorological Institute itself they were co-PIs in the Suomi 100 satellite, but they did not do not yet have purely their own sort of a CubeSat, small sat mission. And so it was an interest from the Finnish Meteorological Institute to, if you will, to try out the small satellite technology and maybe get its benefits, standardization, modularity, and if you find a good commercial off-the-shelf manufacturer using commercial off-the-shelf manufactured components. So in a way, it's a sort of a extension of FMI's direction towards small satellites. Then the 3D printing part is I think it originally started, I could even show it from the pictures. My interest started basically when we noticed early on when we were developing the Suomi 100 how relatively painless it was compared to previous experiences, how it was to quickly manufacture with 3D printing components that otherwise would have taken a lot longer time. So this picture is early on from 2017 or so on, but it's an early picture. But that sort of gave the motive to investigate these 3D printing possibilities further, and we noticed how there's a lot of possibility here. So yeah, to answer Professor Ip your question, it's an extent all these later projects, the lunar mission and 3D printing components is a sort of in a way, at least for my case, a sort of extension from the past lessons learned from the Aalto satellites.
Very good. So here you talk about 50% mass reduction, right? How about cost reduction? Do you also reduce cost that way?
It's a good question. Yeah, this is a good question. Yes, I can't really give a number yet, but it's significantly faster, the process. So if you, for example, count in terms of like funding, how much it takes for like, if you build it in a more traditional way, if you will, it takes time, so it takes funding. But if you can reduce that prototyping time, I'll give you a concrete example. This antenna, the 3D printed code part, we noticed quickly on that there's a huge limitation in terms of how we can put the antennas. So what I did was, draw them in a CAD model, print them out a few times. Then with the other guys, we tried them out, prototyped a bit how we could fit these are sort of a ferromagnetic antennas inside these encapsulated thermoplastic. And this happened, I think, within a few months. And that was it. So roughly maybe 50% in terms of like lead development times would be my cautious estimate. So yeah, it probably will be able to save you some money.
And also increase the reliability, right?
Yeah. Yes, it's another good point. One of the surprising elements of when we have tested these with the vibration bench is that the first idea of people is that, okay, they're plastic, so they probably won't withstand that much. But they can. We have tested this antenna part in a shaker test, vibration shaking test, and we have the earlier parts. All of these parts we have tested in a vibration base. These parts we tested actually like 2 weeks ago, but more recently, and they were able to withstand not only well, but they were able to withstand without any kind of hitch or problem. So it's in a way because it answers to people's worry that okay, maybe these parts will not withstand space conditions or launch conditions, and so it enables a bit to use these fast manufacturing methods without compromising reliability. Yeah.
And in this slide, you wrote that this is a ESA project. So
yes.
So that means in ESA you are leading this effort, right?
I couldn't say leading. There are several other 3D printing projects. So ESA is very interesting overall. We're just one among many that has been developing these 3D printing projects. So they are, it's not about the plastic. It's moreover about actually the 3D printing. So those 3D printing projects, I know at least 3 others in ESA.
So ESA is into this 3D printing for space applications.
Yeah, right. Definitely. Yeah. I've understood also that NASA is, and I would recommend it. Maybe the one draw side is that you have to be a bit careful about the thermoplastic material, because, for example, here in this image, this material is a material called Aalto. So that's the trademark name. I don't remember the actual chemical name, but as you can see, it's very close to the camera. And if it's bad type of a thermoplastic material, it might outgas. And so you have to be a bit careful about choosing the material if you have lenses or something like that, so it doesn't coat your lens and ruin the view. And I'm not really sure if these materials are really appropriate for really sensitive instruments, image instruments. So even PEEK has a bit of outgassing. PEEK is really good in terms of thermoplastic materials. But even it has a bit outgassing, so maybe it's not really appropriate for all kinds of instruments.
Good. Anyone has questions for Dr. Kestilä? Yeah. If not, maybe I ask another question. That's, you mentioned very beginning that one of the spin-off of this early CubeSat effort in Finland is the development of the Ice Eye SAR project. Can you? I mean, I will write to you later. I would like to invite one or two people to give some presentation on this project. Is it possible?
I'm probably not the best person to I'm sure it is possible. I'm probably not the best person to give the presentation. I was involved with it in the early phases, but later on, when they spun off from the university project, they became their own company. So I think they are themselves probably the best persons to present the project. And then the same thing about Reactor Space Lab. So all of these two projects they're the same team. Everybody started in the Aalto 1 project, and then they sort of spun off into their own companies at a relatively early phase. And I would say it's more about, there was a lot of enthusiasm for commercial activities, and it's really good that there is. It's more about the enthusiasm, and the results are to be seen yet. But it is, of course, promising that there is this commercial enthusiasm, because it helps us with, in practical stuff. Like, for example, when we go next time and ask for funding from our funding officials, we can show that, okay, we have some, commercial activities. So there's some larger benefit than the scientific part. For me, the scientific part is close to heart, but for in terms of funding purposes and from larger perspective, it is better to maybe also have commercial activities around these.
Oh, it's amazing having just one or two CubeSat, you launch a space company,
Yes, indeed. That was the case in both spin-offs. Neither had any. At that point, when these spin-offs were created, neither had, I think, maybe. So ISI was created in 2014, and Reactor Space Lab was in 2017. So in both cases, there was really none of the satellites had flown, even in Aalto yet. So there was a lot of goodwill and interest, more than actual concrete results yet. But it's all right. That's how it goes.
Yeah, it's a very good example for the young people in Taiwan to follow. Yeah, and so I will write to you, because I think that you have so many interesting things, to say. I must say.
Oh, thank you.
Okay, good. Since the time is late, 5:05. If no one has questions, I will let Antti go. So Antti, thank you again.
Thank you very much, Professor.
Yeah. Bye-bye.
Bye-bye.